is the minimum value of the true risk that we can hope to achieve. If you look at the curve on purpose, the way I plotted it suggests that my true risk, even over my hypothesis H sharp, is not vanishing. And to better understand why that's the case, we're going to study that in more details, and that will lead us to actually the Bayes classifier. So let's go back to the supervised learning model that we studied before, and I'm going to just rewrite it a little bit to change the notation, in part because we're going to deal a lot with random variables, and there's a convention written in the table of laws of probability that says that random variables should be written in capital letters, which is a convention I'm not following in most of this course, but just for these lectures to make sure that we're not misunderstanding each other's, I'm going to make an effort. So I'm going to redefine my model. It's something that we have seen before. I'm just going to change the notation. So my data set now, I'm going to denote with capital letters. Why? Because the model that we're using says that my data points, my feature vectors, are generated ID according to a fixed distribution Px, which I don't know. And this distribution leads to random variables. So I have random variables x1 up to xn. Similarly, my labels are random variables because they are related to x according to a distribution py given x that in general I don't know. So I again write them as random variables. The loss function I'm going to use here is going to be a binary loss function. There is actually not much loss of generality here in the sense that the proofs do extend fairly easily to other loss functions as long as they are bounded. And I will have you that explore through some homework problems, for instance. Now, with my new notation, we can express the risk, the true risk of a classifier H as follows. It's going to be the expected value over the random variables x and y, which have a joint distribution px, py given x, of the loss, which is this indicative function, h of x not equal to y. And as we have discussed extensively in the previous lectures, it takes here the specific form of a probability. So again, it looks like I'm looking at something that is awfully specific, but the reality is I'm not using much generality because most of these results do generalize pretty naturally using the same kind of reasonings if I go from binary loss functions to bounded loss functions. To answer my question about what is the minimum value of the true risk that I can ever hope to achieve, I'm going to take the point of view that I'm not going to worry too much about what hypothesis set I have to use, but rather, given my data or given what I know about the data, what is the minimum value of the true risk based on a classifier that I estimate from the data? And so the Bayes classifier turns out to be the optimal thing to do, and we can characterize exactly what that classifier looks like. What is the best trick that we can achieve? Well, we're going to cheat a little bit. We're going to first assume that we actually know the distribution px and the distribution py given x. It's an unrealistic assumption because, as I said, if you look back at the definition of back learnability, the point is that we have to be able to learn a model without knowing these assumptions. But from a conceptual perspective, I think you would agree with me that we can do no better than if we had known these quantities ahead of time. And making the assumption that we actually know px, py given x will allow us to actually come up with an explicit expression for the optimal classifier that we could not have done otherwise, which is of course unrealistic because that assumption is unrealistic in the first place, but it will give us a good lower bound on the best risk that we can ever hope to achieve. Keep in mind that all the discussion here will be fairly conceptual. It will be mathematically precise, but fairly conceptual in the sense that it's not something that you would be able to do in practice. Since in practice you never know px, py given x, there's no hope to derive the actual Bayes classifier, but we'll talk about the workarounds about that. What does that mean for practical algorithms? I'm going to introduce a few more notation here. The first one is I'm going to introduce a notation to denote the a posteriori class probabilities of a specific feature vector x. My notation will be the following. I'm going to call eta k of x here the probability that the label y is equal to k, given that my feature vector is equal to x. I'm actually not going to restrict myself to a simple binary classification. I'm going to use a multi-class classification with labels that are indexed by k. I'm also introducing a notation for the a priori class probability. And I'm going to call this a priori class probability pi k. And they correspond to the probability ahead of time, if you wish, that you know that the label is going to be equal to k. Illustrating that in the context of cats and dogs, if you wish, it's like having me saying the probability a priori of having a picture of a cat or a picture of a dog is 50-50, because people who like animals are equally likely to like cats and dogs. And eta k is essentially the probability that given a specific feature vector, what is the probability given a picture that it is a cat or it is a dog? And we're going to assume that these quantities are known here because I'm assuming I know px and py given. Now the main lemma that we're going to establish together is the following. And it's going to tell us that if you design a classifier HB such that HB of x returns a label k that is the maximizer of the a posteriori probability py given x, meaning that here it takes the form argmax over all the labels k of eta k of x. Then that classifier turns out to be optimal in the sense that for any other classifier h, the risk of h, the true risk of h, would exceed the true risk of that classifier, which I call HB. And HB here, in terms of terminology, is called the base classifier. Now, conveniently, it's also possible to estimate exactly what is the true risk of that classifier. And the formula is perhaps intuitive, perhaps not, but it takes the form the expected value over x. Remember, x is a random variable that determines how you draw your data in your data set. Expected value of 1 minus the max over k of eta k of x. And the convention is that this R of HB, the true risk of the base classifier, is often denoted just RB and is actually called the base risk. So again, that result is conceptual in the sense that it really hinges upon us having access to Px and Py given x, which is something that we don't have access to in general. However, we're going to still establish it because it's a convenient way of understanding that given a problem, there is in general a best risk that is not zero, that we can't go below. And we're going to establish that result together. And as you'll see, it's a good exercise in probability. The reason I go operate is because that base classifier actually relates to a lot of problems in engineering that might be interesting. If you ever take a course on coding theory, you will see that that base classifier is essentially the best decoder that you have to implement. You have to do error correction coding. So let's go ahead and establish that result together.